Assalamu alaikum to everyone. I am Muhammad Nan Khan, currently serving as an associate professor at the School of Computing, Skyline University, UAE, and Rifa International University, Lahore campus. Additionally, I hold the position of an assistant professor in the Faculty of AI and Software, Department of Software at Goche University, Republic of Korea. Today, my presentation will focus on the applications of weighted federated machine learning. First, I would like to share a brief overview of my experience in research enterprise. To date, I have authored over 230 articles with a JCN PET factor of 670 plus. The following slide provides detail on my citation information. I have also successfully completed various funding projects in the roles such as a principal investigator, co-PI, and co-investigator, as outlined in these slides. In here, you see that the three projects in which two are successfully completed as a PI. Third one is funded by the NRF Korea. And there's a few projects details in which I'm act as a co-PI. In here, you see that the one project is submitted to the PCU from UK and others. And this is the few projects which were successfully completed as a co-investigator. Now, I will return to the main topic of my presentation, the weighted federated machine learning. Okay. What is the federated machine learning? Federated machine learning, also referred to a collaborative learning, is an innovative machine learning approach that enables AI model training without exposing or sharing individual data. This technique trains an algorithm across numerous decentralized edge devices or servers, each holding local data samples, all which avoiding the need to transfer these data samples between devices. Like in here, the graphical abstract of the federated machine learning. In here, you see that the various organization, you can say that organization 1, organization 2, organization 3, the client 1, client 2, client 3, each client have its own local data. In this scenario, each client train our model based on its local data. Okay, and then after the training, each client share its weights to the server, and then server use some aggregate model which we later on we will discuss, and make a federated algorithm which used for the real-time prediction. This is the mathematical model of federated machine learning at the client end, because in previous diagram you observed that there's a two phases. First is the client end, second is the server end. First we discuss about the client end mathematical model. First we develop a mathematical model of the client end, then server side, and then we simulate these mathematical model using some software like Python, MATLAB, and you achieve your results. In here you see that in here we use the neural network architecture. As you know that the neural network architecture contain at least three layers, at least input layer, hidden layer, and the output layer, and it can be contain multiple hidden layers. Okay, then here W's represent the weights. W is the net of client, CLI represent the client, ith client. In here A represent the weights between the teeth input neuron and the F hidden layer neuron of the ith client, and S2 represent the input of our data, and it multiply, and then C1 is the bias, and in here we use the exponential function activation function. Why we use the sigmoid activation function? Because our output is lie between 0 to 1. That's why we use sigmoid. In case of maybe our possible outcome is between -1 to 1, then we use tan hyperbola. If we output is the real number, then 0, 1, 2, 3, any, then we can use ReLU activation functions. It depends upon your problem to problem. And the second equation in which we use the net of our hidden and out weights between the hidden and output layer neurons. And after that, the last equation shows the error, in which we find out the mean square error. You can use any formula, absolute error, mean square error. A lot of algorithm, a lot of formulas are there, but we use the mean square error formula to calculate the error. After calculating the error, this is a feed forward. Now we want to update the weights, back propagation. In back propagation, we want to update the weights between the output layer and hidden layer, and similarly we want to update the weights between the hidden layer and input layer. The first change in A, we update the weights between input and hidden to output. And in here we apply the chain rule. After applying the chain rule, this is the after simplifying the equations, the final equation is shown in here. Change in B client I between the F hidden layer neuron and the nth output layer neuron equal to eta is a constant, and the lambda is the learning CL client of I, which is represented by this one, and the weight of the client at F naught. Similarly, this is a mathematical model how to change the weights between the hidden to input layer neurons. And these are the final equations which we use to update the weights between the hidden to output to hidden layer neurons, as well as the how to update the weights between hidden and input layer neurons. After that, this is the pseudocode of ith client FML, which run on each client side. In here, you see that there's the three arguments D and A. IH mean input hidden layer weights of the ith client, and similarly B represent the weights between the HO mean hidden and output layer neuron of the ith client. In here, the local data separate into multiple small group of size CS, then initialize the layer input layers hidden layer weights, and we initialize the error of that client equal to 0. And the number of epoch equal to 0. Then for every small group CS, we apply the feed-forward phase in which we calculate the W of each client, which shown in previous slides, and we calculate the out of the X of that client using equation 5. After that, we calculate the error using equation 6. After calculating the error, then we update the weights. Feed-forward phase is initiated. In here, we use to update the weights between the hidden and output and hidden layer neurons, and using the equation 13. And similarly, we want to update the weights between the hidden and output input layer neurons using the equation 18, which shown in previous. And then we update the weights with the help of equation 20 and 21. And if the stopping criteria not met, this step is executed again and again. If our stopping criteria is met, then it stop and it return back the optimum weights of that ith client between the input and hidden layer, as well as the weights between the hidden and output layer neurons. Now we are talking about the server side. Now each client, maybe in our case 3 clients, 4 clients, or 5 clients, each client send the weights between the input and hidden layer, and that is in the form of matrix. In this case, we consider 3 clients: CL1, CL2, CL3. And here you see that I mean the input and hidden layer between the weights is represented with A. Its dimension is D1 into D2. Similarly, the client 2 in where we use the BR algorithm, which transmit the matrix with dimensions D3 and D4. And similarly, the third client send a weight matrix which dimension is D5 and D6. There are 2 cases. One case, if all these clients they use different data definitely and different algorithm. In here you see that in previous slide, the first use the LM, second use the BR, third use the scale conjugate. Okay, maybe the number of rows and columns are same. If the all 3 clients number of rows D1, D3, D5 are equal and similar number of columns are same, then we can add all these weight matrices in here. But if the second case, if number of rows or columns are not equal, then you're not able to add these matrices. Then first you resize their matrix size and equalize all those matrices dimensions. How? First we calculate the maximum between the rows and columns, then we create a 0 matrix of that dimension, and after that we horizontally concatenate of previous matrices and this 0 embedded matrices, and then after that the matrices size are same, then we can add all those matrices. In here you see that, and we use the term weighted on the basis of error, on the basis of accuracies depend upon you. In here you see that the first client weight is 1, but for the second we use its weights is 2 multiple to weighted. In here we not give the same weight of each client, we change the weightage. The first client weightage is 1, the second client weights is multiplied by 2, and the third client weight multiplied by 0.5. Depend upon your error, your accuracy. Based on that you can set these weightages, and then you calculate the weights between optimum weight between the input and hidden layer of federated server. And similarly you can perform all those steps to find out the optimum weights between hidden and output layer at the server side. This is the pseudocode of the server side, and here you see that we receive the different input from the client side. First, we initialize the input matrix at the server side between the weights between the input and hidden layer, similarly hidden to output layer. Then in here you see that each client return two things. Okay, and then we calculate the BHOFS using the equation 47 previous, as I told you, and 34. And after that we predict the unknown samples using these two equations, and then we calculate the error and then stop. In server side there's only feed forward step, there's a no back propagation. Okay. Okay, now we are talking about the two real-time applications which I consider today. Number one is hydrogen storage prediction. In the context of the smart cities, weighted federated machine learning proves instrumental in optimizing hydrogen storage, ensuring a stable and sustainable energy supply. Through real-time data aggregation and analysis, weighted federated machine learning enhance the accuracy of the hydrogen storage prediction, enabling efficient utilization of the clean energy resources in urban areas. In here you see that this is our one of the funding project funded in Gaussian University. In this article, we use a real-time data which we collect from our university, different sites of the university and industry as well. In here you see there is a three different locations where we can acquire the data, because in here we use the different sensors. They transmit the data through wireless link, maybe noise is added first. That's what we call the raw data. First we perform the pre-processing to mitigate these noise. After that we're applying different algorithms on different sites. After that we check the initial learning criteria of meet at that client, and if yes, well and good. If no, then retrain that algo and change its parameter settings. If all meet the initial criteria, then they transmit their weights, and we make an aggregate federated machine learning, and then we store on a cloud. And then in real-time data we can send our sensor sense the data and transmit, and we import that stored train model, and we give that input to that, and it predict whether it is because in this problem we have the three classes, low, medium, high. According to that we decide if the hydrogen storage is low, maybe we provide to a homes. If it is a medium, then we may provide to a gas stations. If it is a high, then we provide to an industry. According to their decision, according to their output, we decide where we forward or take the decision based off our output. We will consume that hydrogen. This is the simulation results. As I told you, that we have the three classes: low, medium, high. When we apply the federated machine learning, weighted federated machine learning on these classes, in case of low, we achieve the 96.5% accuracy. In case of medium, we achieve the 99%, 99.9 accuracy. In the case of high storage class, we achieve 96.4. And the other parameters also shown in here: misclassification rate, sensitivity, selectivity, and precision. And this is the overall accuracy of our prediction of hydrogen storage use empowered with the federated machine learning, and its accuracy is 96.4 and misclassification rate is 3.60. Now I am talking about the second application, that is the smart health or the healthcare 5.0. The healthcare sector within a smart cities benefits for dynamic weighted federated machine learning, offering personalized and responsive medical services, incorporating the real-time patient data from diverse sources. Weighted federated machine learning empowers healthcare professionals to make timely decisions and deliver precision medicines. The application of weighted federated machine learning in healthcare is used to monitor the disease. Monitoring enables smart cities to enable public health initiatives and resource allocation. And this is a graphical model of our secure healthcare system, which is also funding project. In here you see that we shows multiple client end, means every hospitals contain its local data, and that hospital train their model on the base of their available local data. After that, each hospital transmit its local weight, not data, just weights to the server. Means in case of data, you assume that each hospital contains a terabyte. Okay, and it takes a huge of time to transmit all data from client to source. It's consume bandwidth. Instead of that, we just transmit the optimum weights, which may be in kbs, which in few seconds they transmit from the source to destination. At a server end, we aggregate the model on the base of these clients, and which we use for the real-time prediction. Okay, this is a detailed model which we already published in 7 impact factor paper. Okay, now we move toward the results of the smart health application. As I told you, we use the 4 hospital data. In this, the accuracy of the each hospital, H1 hospital, this is the training accuracy of individual hospital. That is the training accuracy of the hospital. One is 93.75%. Similarly, in the H2 client 2, you can say that is a 94.72. Similarly, hospital 3 is 97.75 and hospital 4 95.72 accuracy is achieved. Then these hospital transmit the data, and this is the validation accuracy at the client end. Okay, 95% accuracy at hospital 1, 93.5 accuracy at H2, and 96.5 accuracy at client 3, and 94.5% accuracy at hospital 4 at client 4. After that, we transmit all those optimum weights to the server, and we make an aggregate model using the previous mathematical model which I shown you, and you develop aggregate model, and then you give the unknown real-time data to that aggregate model, and they predict the accuracy. Okay, and in here you see that the aggregated model server and its prediction accuracy is 97%, which is higher than as compared to our individual hospital, because maybe H1 contain the more data of the type 1 patient, maybe H2 contain the more data of type 2 patient. But when we aggregate all individual models into a one model, so its learning is more better as compared to individual models. That's why its accuracy is too much high as compared to previous one, which is 97%. And similarly, the sensitivity, specificity, and other statistical parameter analysis is also shown in here. This is the comparison of our this healthcare application with the previous published articles, which clearly shown that our proposed model shows that better accuracy as compared to previous. And this article is already published in CIBM, having impact factor 6 plus elsewhere journal. Okay, the other application area, you can apply the federated machine learning in cybersecurity. Our few articles are submitted in transaction as well, where we apply the federated machine learning, weighted federated machine learning cybersecurity, and you can apply on smart traffic, wireless networks, smart agriculture, and a lot of other applications where you can apply this weighted federated machine learning. Thank you.